All right. Now we are mastering the space-time. Let's start to work with physical objects. Okay? So now I'm going to look how to manage particles with and without mass. Okay? Therefore, specifically, I'm going to use just matter particles, some massive particles, whatever they are, and photons, for instance. Okay? But that's true for any massless particle. And we are going to study their dynamics. Okay, good. So we have the 4 space, we have our 4 vector, we know how to deal with it, right? We have seen already, just by drawing, what are the world lines, which is the name we use to describe trajectories in the space-time, in our 4-dimensional space-time. And in general, you label the x mu position. So you have this x mu, your object is in this location, given a certain lambda, where lambda is an affine parameter. Okay, I'm not going into detail with that. I'm going to show you later on why. For example, for a massive particle, we could use the proper time. This particle moving is experiencing its own clock, and we can define the location of the particle using the clock of that particle, for instance. So for the moment, let's speak about massive particles. Let's use our affine parameter as tau, the proper time. Proper time. Nice. What we can do then, we describe the forward velocity now, which is defined. I can call it u mu, v mu, use the whatever letter you want. But in any case, is defined as the derivative of the position in the Minkowski space with respect to the tau. Okay? That's the velocity of the particle using its clock. That can be related to your own clock if through the Lorentz transformation, and as we have seen, there is a gamma factor which is popping up. Okay? So we have a relationship with your own time, not the one of the particle. Then as a vector, so if we stitch together all the components of our 4 velocity, that's equal to gamma c dt over dt, dx component 1 over dt, dx2 over dt, dx3 over dt. And I didn't use transport, so no transport. Tlac, tlac, goes away. What is this? That's the standard velocity, right? Therefore, we have our gamma, c, which is left, and then we have the velocity of the particle. Or, if we want to, collect the c factor in front of the expression, we can also write it like this, right? V divided c is our beta, as we have seen. Now what we can note, this is just a vector as x and so on and so forth. And vectors are not covariant. Are not invariant under Lorentz transformations. The components are changing, right? That's the point of the transformation that we used. But their norm does not. Okay? I stressed it 100 times in the previous hour. And if we are taking the 4 velocity and I compute the norm, so just to see how much is the amplitude of the absolute value of the velocity, squared in this case, you can also write it as u mu. And again, just to be a little bit repetitive, to let the concept sink in, we can also write it like this, where we have our metric. Now we can use this expression, right? We can plug it here. What are we going to get? We are going to get our c square gamma square, c square gamma square, because I'm multiplying this is just a scale factor, and I have twice multiplied, so that's what we get. And then we have the other component. Minus 1 plus beta squared. Minus because of the metric, and then we have beta squared. So that's 1 to the power of 2 minus because of the metric, and beta to the power of 2. And you see this is a scalar. We started with a vector, but that's the norm of that three-dimensional vector. So it's a scalar. What is it equal to? Well, we look at this guy. How does it look like? It looks like a lot like gamma, but to the power of minus 2. Therefore, this guy and this guy cancel out. Ooh. What is it equal to? Is equal to minus c squared. Well, it's minus gamma, sorry. Yeah? Yes, it's a 3 vector. Because it's this guy here. So that's x, and that's v, which is a 3-dimensional object. Oh, sorry? Yeah, but look, this is a 4-dimensional vector, and you can think at it as one component and then as a vector. And you cannot apply the Lorentz transformation to this guy, for example, because it belongs to a vector space of dimension 3, not to a vector space which is the Minkowski one of dimension 4. Two different things. Okay, so the minus c is there, and the only thing that is left is the c squared. Look, it's a constant, which is invariant. It doesn't change. So all 4 velocities are equal to c squared, and look, that's it. Okay? Invariant. What happens if we go in the rest frame, just to give you a simple example of that particle? Rest frame of particle. What happens? What's going to be? P. 0. Right? Therefore, our u prime, I can define a frame in which, and I call it u prime, and I use the one of the for the particle, which is equal to that. Very simple. Okay, that's handy. So this sort of transformation going the rest frame of some particle, for example, is very handy because this all drop. Okay, it all disappears. Then we can move on and build up on the 4 velocity. We can construct the 4 momentum. In analogy of non-relativistic mechanics, we can define this guy simply as the mass, the rest mass of our particle, so the mass of the particle at rest, so if we would measure its mass in its own rest frame, is equal and is multiplied by the 4 velocity. That's it. Okay? Then let's give a look again at the component of this guy as well. And what we do, we just use the definition of the 4 velocity, nothing else. So we get this expression, and we plug it into here. What we get is our gamma m0 c plus m0 and the velocity of the particle. So let's give a look now at the components. Component 1 and then the 3 components that I summarize with these 2. What are they? Well, we have gamma m0 c. That's this one, right? Gamma m0 c. Let's now make the gamma factor explicit. We have m0 c, 1 minus beta squared minus 1/2. And now I can use a Taylor expansion, right? Because beta, yes, is a particle, but let's take a non-relativistic particle for simplicity. And this guy is very small with respect to 1. I can Taylor expand this expression. Therefore, that's approximately m0c, so this guy is just a factor. 1, I didn't touch it, minus, minus, and there is the 1/2, which gives us a plus 1/2 beta squared, and then there will be the higher order terms. Fantastic. What do we realize looking at this expression? We can just continue and start to investigate what's the meaning of these various terms, right? This doesn't look, the momentum is there, but I don't know, it's weird. There is something strange in it, okay? So let's investigate even better. Let's make the multiplication explicit. So we are going to have our m0c plus 1/2 mc. Then we have, on the 1/2 we already used it, so we have the velocity square over c squared. I'm using the c squared which was hidden there. And then there are the other terms. Okay? And let's group 1 over c. I'm really going to all steps. Plus 1/2 m0 v squared plus the other terms. Oh, now there is something familiar. 1/2 mv squared. That's kinetic energy. Ooh, we're starting to get some physical meaning. What are the units? That's the units of an energy. What must be the unit of this guy? An energy as well. That's the rest energy of our particle. The particle at rest, doing nothing, just because it possesses a mass, it has an inner energy. Popping up by that. Wow. Okay? Then we can also start to look at further properties of the momentum. Let's investigate even in more detail that by using this expression. So by doing this realization, that's an energy, the term dual. Let's just take the term number 2, which is, let's keep it here. Just for convenience, let's write it here. We have P equal to gamma m0v. You see? What do we have? P is this expression, right? What are the units of gamma? Known, no units. What is this mv? Well, they are the units of a momentum. So that's the momentum of our relativistic particle. Here we have energy. And here we have the momentum. That's the energy momentum. So in special relativity, we don't speak about anymore about energy and momentum as two distinct things, but we have one individual mathematical object, which is a 4 vector, which is the energy momentum. That's one thing. Okay? That's important. And therefore, we speak not about energy conservation and momentum conservation, but we speak about energy momentum conservation. Okay? That's a key step. That's a key change in the way of dealing with objects and perceiving objects. Now let's give a look again at the scalar product of this guy. So again, we investigate the norm to look for invariant quantities that characterize our particle. We just apply the scalar product, as we already did, using this expression, knowing that we are dealing with the energy divided c for the first component, and the momentum with our gamma factor there. So what we're going to have is E squared over C squared plus P squared. Or, if we want, we can play the same game by using the contraction with the metric P mu mu, as we did earlier for the other vectors in general, right? And we use now this definition here, okay? And therefore, I just plug this guy into here. What we get? A constant, which is m0 squared. And then we have the norm of the 4 velocity, because we have u mu, u mu. What is it equal to? Minus c. That's what we found earlier. sorry, squared. Therefore, that's equal to m0 c squared with the minus, which is, of course, invariant. But these two guys are the same thing, so they must be equal. Let's equate the two. Let's put them together. Therefore, we are going to have minus e squared over c squared plus e bar squared equal to minus m0 c squared squared. We have an expression for the energy. From this guy, we can basically get e squared equal to m0 c to the power of 2 plus c squared p squared. We have the energy, full energy of the particle, with its kinetic term and its due to the momentum. So that's the energy content of the momentum, and that's the rest mass of our particle. What we are going for photons, m equal to 0, because we know are massless. And I'm going to show you that through arguments given by special relativity, photons must be massless. So you are going to derive that. But you know it by memory. For photons, that's what we have. Okay? Beautiful. Okay, that's it for the momentum. Yes. Let's give a look at photons then. Okay, there is a key difference here, and the problem is here. Photons are moving along the light cone. And what do we have? What is the Fourier interval along the light cone? That's equal to 0. Right? We have seen that. That's where we started. That was our starting point. How is defined the proper time? If I have c squared d tau squared, in the rest, we are in the rest frame of the particle, we have this expression. But that's equal to 0. Right? Therefore, d tau squared is equal to 0. The tau is not defined. Ui, ui, ui. Therefore, I cannot use this expression for the four velocity. I cannot write the x mu over the tau. I cannot. And if I cannot write like this, I cannot even write that. We have a problem, okay? But that's easy to solve. Okay? P mu equal to m, which is, by the way, equal to 0. But still, we don't know that. But you know that is equal to 0, so that's already a problem. X mu over the tau doesn't work. Okay? More from the fact that the mass is equal to 0, so we would have always no momentum, which is nonsense, because we know that photons have it. But the problem is mathematical, and it's here, because the momentum, the photons are moving along the light cone. Good. So what we can do? What we can do is to make a step back and forget about the proper time and use just an affine parameterization lambda, which is not our proper time. It's just something that marks the point along the word line of our photons, along the light cone. Our affine parameter. Therefore, going back to our discussion, we have our four-tile interval, is our nu, and we have the x mu, the x nu. We can, now I play the dirty physicist trick, in which I can do that, right? So, dirty physicist, I can divide by the lambda and multiply by the lambda square. Okay? Nice. And now I can define these two guys, not as the 4 velocity, because it's not based on the proper time, but on something else. Let's call it k. So we have our metric, nu mu, k mu, and k nu in the lambda to the power of 2. We call this k, which is defined as k mu over the lambda as wave vector. You see, it's parameterizing the position of the photons along the light cone. Because again, dirty trick, I get the lambda on the other side. I can see what is the step in the position once I multiply our the lambda with k mu. What are the properties of the k mu? Well, it's marking the direction of motion of the photons, which is along the light cone. So it must be a null vector. Okay? Then what else can we do? Well, we can look at the components of this guy, k mu equal to minus k0 to the power of 2 plus k1 to the power of 2 plus to the power of 2 plus to the power of 2 for the other two spatial components. And again, as we did before, earlier, we can split it in a time component plus this component. And this must be equal to 0 because it's a null vector. Therefore, we get that the k0 component is equal to the modulus of the k component of the space 1. And therefore, I can write all the components of my k mu. Let's call it k0, so I can use this one as the normalization factor for my vector, 1 and e, where this vector here is marking some amplitude related to the 0 component of my 4 vector and the direction of propagation of my photon, where this is it's a vector with a unit modulus, okay? Now I don't know if I have the time, because now, yes, I have it. Now, having this new instrument at hand, this guy here, you see we can construct something which goes in the direction of having the momentum definition for our photons. Let's do it on a clean board and do it below here. Gesundheit. So with this k, we can now characterize the momentum of a vector, of our photons. Let's do that, and let's just recall what we realized for our momentum, for massive particles. What we want to do is to have a construction such that what we base on the k vector keeps this shape, such that from the 0 component we can identify an energy, and from the other 3 spatial components we can identify a momentum, a 3-dimensional momentum. Okay, so what we can do? Well, if it's as an object with mass 0, we can use this expression, and we realize, so it's a null vector, and it therefore is massless. That's equal to Cp. Okay, so we know we have a relationship between momentum and energy. Yeah. So then what we have? We have quantum mechanics. And quantum mechanics tell us what is the energy of the vector. We know, or the photons. We know that photons do have an energy, right? That is related to their frequency. That's radiation, right? Photons, they also have a frequency. And the energy of a photon is h nu. Or if you want, if you wish, it's h bar nu omega. We can put the two things together. Cool. Therefore, P is going to be equal to h nu over c, or if we are using the h bar, it's going to be h bar omega over c, which is equal to, yeah, well, that's it. And if you want to link it to the frequency, to the wavelength, sorry, you can also write it like that. Okay? Nice. Here, of course, I just recall you the definition that omega is just nu over 2 pi, and the wavelength is just defined as the speed of light divided the frequency of the photon. Let's now make, we know what is the energy, how we can relate it to the frequency of our photon. Let's go back to our K and to definition of our momentum such that we can combine them together. So let's do that. So we have our P mu. I just write it again here such that you have it together. P E. That's what we have. But now I use this vector, you see. That's the modulus of the momentum along the direction of propagation that is the one of K. Okay? Then I just take out this scalar, which is E over C, and then we have 1 over E bar. Hoo-hoo-hoo. Look at this object. Look at that object. There is an equal missing here. Equal. Okay? Look at this guy. Look at this guy. Look at this guy, K0. Look at this guy. Ho-ho. We had the very same expression. So the fourth frequency can be expressed, represents the momentum, the fourth momentum of photons. So using now this expression for the energy, where is it? Here, right? We can plug it here. And what we obtain is h bar omega over c 1 E bar, which is also equal to h bar, and then we have our fourth frequency K. Momentum for frequency. You see, we introduced physics, omega. That's something we can measure. Right. Then I use the fact, actually here, I use the fact that the mass of the photons is equal to 0. But I can read it on Wikipedia, right? Now, using this discussion, how can I say that? Let's give a look. Let's give a look. And everything is again in our four momentum that now I have defined. We have P mu, and we know that this guy is equal to 0, right? Because we're moving along the four dimension, the four momentum. And P mu, we already computed up there. And what we obtain, if we plug in our expression for the photon, where is it? If we plug in our expression of the momentum, we get E squared equal to C squared, P bar squared. Okay? Oh, what's the difference with respect to that expression up there? We have up there, for a generic particle, where we included a mass, we had plus m squared c to the power of 4, which is not appearing. What does it mean? That this guy is equal to 0. So the fact that the particle is moving along the trajectory, whatever the particle is, it means that it has a zero mass. That's implicit. That's coming out from the fact that we are moving along the light cone. Okay? I think that's another astonishing thing that is coming out, but it's very, very simple considerations. Nice. So we can conclude here. What we did was to look at the dynamics of particle and start to define physical quantities, such as 4 velocities, 4 momentum, and characterize the particles in terms of their energy. And especially, that's key point here, that we identified the 4 momentum as comprising the energy of the particle and the momentum of the particle in one individual object, with the consequences that I said. Then we gave a look at photons, because here we were focusing on massive particles. Here we are looking for photons that are moving along the light cone with the difficulty that the proper time is not well defined for photons. Okay? The tau is equal to 0 there. We can use it. Therefore, what we did was to use just a generic affine parameterization to characterize its location along its trajectory. And we introduced the wave vector that then, thanks to then we could link to the general definition that we had earlier for the massive particles, such that we can easily identify a component which is given by the energy, and a component, so let's do it like this, a component which is related to the energy, hence, through quantum mechanics, the frequency associated to the particle, stuff that one can measure, and the momentum of the photon. Okay? That's what we did. Next time, we are going to deal with more complicated objects, because this is a particle, cool, but it's one. Okay? Therefore, what we need to do is a more powerful instrument to deal with collection of many particles. And a vector to describe collection of many particles is not sufficient, because a particle can move in one direction. That's the for which a vector is sufficient. But for a particle moving in another direction, we need something that can point also in another direction. And if we have zillions or billions or millions zillions of them, we need something that can deal with all possible directions. Okay? This is a tensor, and this is going to be the energy momentum tensor. What you want is a generalization of the 4 momentum that we have seen here. Okay? More powerful than that, as we are going to see. It can also be used not only for particles, but can also be used for fields. And that's going to be fundamental once we are going to describe dark energy, for example. Once we are going to describe the inflaton field and other stuff that we are going to meet during the lectures. Okay? So also next time is going to be very important to define this guy. And once I've done that during the first lecture, we will start with general relativity. Okay? And we will derive the Einstein fields equations. Good. Thank you very much. That's it for today. See you next time.